Hey, it's Horner, and we're going to do 2003 AP Physics. Remember, this is really AP Physics 1. We've modified these problems to make it more like AP Physics 1. This is Form B, number 1. We have an airplane that's accelerating. So you're sitting inside of this airplane. So I'm just going to draw the front of the airplane. So there's the airplane. You are sitting here inside of the airplane. And there is a string that originally was hanging down, but now the airplane is accelerating in this direction. And so that string kind of comes back and you see this little washer that is looks like it's coming to you. So there's an angle right here in the whole shot. So that's kind of a picture of what it should look like or what's going on. So it's a little different. In the space below, they want us to draw a free body diagram for the ring. So we're going to go ahead and put in our mg here. And then there's got to be some sort of tension right here, and it's T. And that's it. That's all there is to that part. So this is 1 point here, and most likely 1 point right there. The next thing that they want us to do for this problem is we're going to go through and determine the acceleration the minimum length of the runway that is needed for the plane to take off. So they reach takeoff speed at 65 meters per second and they accelerate for 30 seconds. So it takes a little while. So we have to figure out how much runway do we need. Let's first figure out the acceleration of the plane. As long as it's uniform acceleration, we know it's delta V over delta T. The numbers here would be 65, and that's meters per second over 30 seconds. And so our acceleration is about 2.17 meters per second squared. Now there's two ways to do this problem. We can either use the second kinematic equation, delta x is equal to VOT plus 1 half AT squared, or we can use the third one, which is VF squared is equal to VO squared plus 2 times A times D. Here we're going to solve for delta x. Over here we would just solve for D. So either way you do it, you should get exactly the same answer. Just do it one way though. This is equal to our original speed on takeoff is 0 plus 1 half of the acceleration, which we said is 2.17 times our time, which is 30 squared. Over here, our final velocity, be careful, this one is 65 squared, is equal to 0. So there's our VO, plus 2 times, and we're accelerating, so this is positive, 2.17 times D. If we solve either for delta x or we solve for D, we're going to get the same thing, and that is 975 meters. So that's the length of the runway that we need in order for this thing to take off. The next one is to find the angle the string makes with the vertical during the acceleration of the plane before it leaves the ground. So let's think about a free body diagram. We know that we have our washer, and pointing straight down is mg. Then we have a tension, and that tension goes up and to the right, and it's T. And so if we think about an axis going left and right and up and down, this is plus y, this is plus x. Now there is something happening in the x. It's accelerating. And because it's accelerating, we're going to just say that there's a positive acceleration to the right. So we need to do a couple things with this diagram. Let's draw our components. This angle right here, we're going to call it theta, because that's the angle they gave us in the original problem. We have our opposite side and our adjacent sides. Remember, opposite is sine, so this is going to be t times the sine of the angle. And over here, this will be t times the cosine of the angle. So up and down is t cosine of the angle, left and right is t sine of the angle. For this one, we need to do some of the forces in the x direction. And if you think about it, going left to right, it is accelerating. So this would be mass times acceleration. And then the sum of the forces in the y, it's not accelerating up and down, just left and right until it takes off. So this is before it leaves the ground. Otherwise, this would be a very difficult problem to do. We know that in the x direction, we have t sine of the angle. We don't have anything in the negative x, so that's just equal to ma. And then in the y direction, we have t cosine of the angle minus mg is equal to 0. So here we've got t cosine of the angle is equal to mg. So now we have a couple of different equations. we need to put these two equations together. So let's solve this one for t. So this one's t is equal to mg all over the cosine of the angle. And now we can take what we have for t, which is this, and we're going to plug it in over here for t. So now we're going to have mg times the sine of the angle all over the cosine of the angle, and that is equal to ma. Sine over cosine is tangent, so we're going to have mg times the tangent of the angle is equal to ma. Notice our m's actually do cross off, and we're going to be left with the tangent of the angle is equal to a over g, but we need to derive an equation for the angle, so we want the angle by itself. So that's equal to the inverse tangent of a over g. And that is the final equation for this part. The very next thing they want us to do here in letter D, which is the very last part, is to figure out what is that angle. Oops, went too far there, and we want to find out what that angle is. So we're going to use our equation from C above. So remember, our angle is equal to the inverse tangent of A over G. And so this is equal to the inverse tangent of 2.17 divided by 10. And if you do that math, you should get about 12.2 degrees. And that is the end of this problem.